Okay, good afternoon. We're getting ready to start our next session. I'd like to introduce Sergey Dorodnicov from Intel RealSense. Just by an aside, Intel RealSense camera last year won the Vision Product of the Year award for best camera. So it's a really cool device and has some really powerful capabilities. So with that, I'd like to introduce Sergey.
Thank you.
Okay.
Thank you. So welcome. This is Applied Depth Sensing with Intel RealSense. I'm Sergey. I'm managing our SDK on GitHub. In this talk, I'm going to show the applications of depth sensing in robotics. We're going to see one simple way you can assemble a working localization and mapping pipeline using open source components. We'll discuss the limitations of this approach and possible ways one could improve it. And finally, I'm going to show our own take on this problem in form of our standalone SLAM solution, which we just released a couple of months ago. So this is new. With that said, let's begin with an overview of what is depth sensing and what differs a depth camera from a regular webcam. So in addition to the regular RGB information provided by a webcam, a depth camera is also providing a layer of depth with every frame, which contains for every pixel its distance to the camera. Using this information, you can think of every frame from a depth camera as a standalone snapshot in 3D of the environment, capturing the geometry and the distances in the environment. There are several talks in this conference about different depth technologies. In fact, there's another talk about depth in this very room after this one, so I encourage you to see it. But for the purpose of this presentation, I'm going to talk about our D400 depth cameras. So RealSense D400 cameras are a family of stereoscopic depth cameras. They share the property of being able to operate indoor as well as outdoor, including in bright sunlight. Due to stereoscopic nature, the more light you can throw at it, the better. It provides reasonable accuracy within several meters. In addition, it suffers from no multi-camera interference, so you can have as many of these as you want in a single environment. And it operates at relatively low power. It is roughly 1.5 watt to operate the camera. It's powered by USB. So these devices were introduced to the market early last year, and we have been supporting and expanding this family since, with new models coming up and new features being added all the time. This technology has a wide range of applications. Specifically in robotics, it is used for localization and mapping, which we're focusing on in this talk. And it is a critical component for indoor navigation. In addition, 3D information can be very useful to avoid obstacles in 3D space and not just on the plane, on the single plane. So this can be useful, for example, for a drone to avoid collisions. Next, scene understanding can be enhanced with depth, Let's say you have a robot and you're trying to detect a cat. So you would run some kind of inference on your edge device. Maybe you're running OpenVINO or any other neural network. Then you can use the depth information to make sure that what you detected is actually a real object in the 3D space and not, for example, a picture of a cat or just an artifact, as you know that networks sometimes see things where they're not. So that's a very common use case. Measurement and manipulation are also applications that are related to mapping. And finally, you can use depth and gesture recognition to communicate with your robot. To give you a more concrete example, this is from last year's IROS. The two robots are trying to pick up objects and are based on very similar platforms by Heavy Robotics, with the main difference being that one of them is operated remotely by a human, and the other one is completely autonomous, driven by a RealSense camera. So can you guess which is which? The future is automation. Another component very important for robotics is the inertial measurement unit. An IMU is a collection of sensors, usually containing an accelerometer and a gyroscope. The accelerometer is measuring the total force acting on an object at any given time, and the gyroscope is measuring the angular velocity. Using these two inputs, we can run them through a simple filter and estimate the orientation of the device in 3D, as well as get some basic sense of local motion. We have added IMU capabilities to our D400 family of cameras last December in form of our D435i device. Now let's talk about the software components that we're going to need to build something useful from this technology. First, we need a way to talk to the camera. Fortunately, we have an open source SDK. We're on GitHub, and we're working with small but growing community and encourage third-party contributions. The SDK is running on most common operating systems, except perhaps iOS. And we have integrations with many different languages and technologies. To name a few, we have examples for LabVIEW used in education and industry. We work with Unity 3D, and people have very cool interactive demos using our technology. We have support for MATLAB, and for the purpose of this talk, ROS, the robotic operating system, is going to be very useful. So ROS is a collection of tools that helps robot developers make robots. It runs on Ubuntu platform. And we have support for both ROS 1 and ROS 2 with RealSense. The next component that we're going to require is a visual odometry system. A visual odometry, or VSLAM, is an algorithm designed to estimate the location and the orientation of the device in 3D space based on features in the environment, while at the same time updating and maintaining a map of these features as it goes. This is somewhat similar to the idea of navigating via the constellations, in that it relies on triangulation. And there are many free and commercial SLAM solutions available. Here are some of them, but here I selected to talk to you about one of them called RTubMap. RTubMap is a free SLAM solution. It's extremely robust. It can run on top of pretty much any depth camera on the market, not just RealSense. And it can even operate on top of a classic stereo solution without really requiring depth. And it has the capability of loop closure, which means that when the robot is finishing a loop and it sees features it has discovered before, it will understand and update its location, but also backpropagate this information to the map it is building. And we'll see an example of that. So RTubMap is also available as a ROS package. So you can download it, give it a try. And when you start to compare visual odometry with IMU aggregation, you see that these two technologies are related and complementary to each other. So the IMU data is available at much higher resolution, at a much higher frequency. It is usually coming to you at several hundred of samples per second, while the visual odometry takes more time to image to be acquired and processed. However, visual odometry is relatively stable because it relies on external features, and the IMU is susceptible to aggregated drift over time. At the same time, if you have no features, you don't have any visual odometry. So the visual odometry solution is somewhat scene-dependent, with the IMU being more robust in that sense, unless you put it on like another planet or on a rocket, which people try to do. And finally, the IMU aggregation requires much less computational resources compared to the visual odometry. So the natural question is, why not have both? And this is exactly what we're going to do. We're going to take the RGB plus depth data from the camera and pass it through RTubMap. And we're going to take the IMU data and pass it through an IMU filter. In this case, we're using the Magic IMU filter, also available in ROS. In addition, we're going to introduce a higher level Kalman filter node so that the camera transform will get updated in high frequency with the IMU samples, but then get corrected every once in a while from RTubMap. This whole process is documented as a tutorial on our GitHub, and you can get the link by scanning this QR code. Also, the slides and the presentation will be available. The idea was to make this process as easy as possible for everyone to just grab a device and get going. So let's see how it performs. On the left, you have the feed from the camera, and on the right is the 3D map it's building. So here we have a wheeled robot navigating in a dense cubicle area. And you can see that as it kind of turns over corners, there is some inconsistency and some drift being aggregated. Now, this is done using the 35i depth camera with RTubMap and the Intel NUC platform. when it comes and sees the loop, here is the point of loop closure. After loop closure, the accuracy of this scan is pretty nice, but prior to loop closure, this is something like 200 feet, and the drift was varying between 1 to 20 feet between experiments. So what are the possible ways we could improve this? First problem that this has is that we need to be very careful going around corners. So in this example, you can see that we are approaching a corner, and the camera is mostly staring at the blank wall, and we're relying mostly on the IMU data, so the smallest bump in the accelerometer just sends the tracking spinning, and we completely lose ourselves. The way to recover, you could backtrack and let RTAB map understand where it is, but it's not great. So there are a couple of ways we can improve this situation. One way is by increasing the field of view of the camera. So by having a wider field of view, we will get more features in, and it will be harder for the camera to get blindfolded, essentially. Another way we can address this is by improving IMU calibration. And with improved calibration, you can rely on the IMU data for longer. The second problem with this approach is the aggregated drift prior to relocalization, but also the overall tracking accuracy. However, this is just a couple of software open source components that we took off the shelf without any fine-tuning, without any parameter optimization. So if you're willing to invest more time into optimizing it for your specific use case, you will no doubt get much better results. But the cost, of course, is your time. And finally, running visual odometry on the CPU can be pretty heavy and sometimes prohibitive on some platforms. So instead, it would be nice to offload this problem to an external hardware accelerator. One example of such an accelerator can be the Intel Movidius chip, which is designed for low-power computer vision. And these steps are exactly what we did with our latest tracking camera, T265. We took custom, well-optimized SLAM algorithm, and we ported it to a low-power compute and paired it with a set of high-quality sensors that were selected specifically for the problem of tracking. Here's the same example from before. Now we're still using a depth camera for mapping, but the entire problem of localization is being offloaded to the tracking camera. And with the wider field of view and better calibrated IMU, this solution is both more robust and more accurate compared to the naive approach. In fact, as it is closing the loop, it's hard to even see the point of relocalization. With the system producing somewhere around 1% of drift prior to relocalization. Please follow us at realsense.intel.com. We continue to develop and design new cool computer vision sensors. And also special shout out to our hosts, the Embedded Vision Alliance, for putting this awesome event together. Here is some extra reading material. And if you want to see the T265 or the D35i cameras in action, come visit us at our booth. We're just by the entrance. And that's the talk. Thank you so much. I will be happy to answer any questions.
Thank you, Sergey. We have any questions for Sergey? If you do, please step up to the mic.
That was an interesting presentation. The second, when you repeated the demo, you said you still use a depth camera. The depth camera is part of the T265, or is it separate?
It is not part of the T265. The way we see it, the tracking problem requires wider field of view. Mm-hmm. But if you're trying to do depth from wide field of view lens, the depth quality will inevitably degrade. So this is why we decided to split these two devices into two different families.
Sure.
And this allows to people to pick and choose what is right for their application. Some customers don't need depth or don't need tracking, so sure. They can.
Yeah, that makes sense. So the depth camera was in the second demo was a 435 as well, though, or what did you use for the depth camera?
Yeah, I believe so.
Okay.
But it was not using the IMU. Basically, it was connected. Again, we have the setup in our booth. It was connected rigidly to the T265. So the depth was going to RTAB map as the point cloud data. And we basically overridden the odometry input to the RTAB map to make it use the odometry from T265 instead of doing its own thing.
Okay.
So this was the configuration.
All right. Thanks very much.
Thank you.
Hi. If we want to design our own customized SLAM algorithm, can we grab the raw data from T265?
Yes. The module provides two fisheye cameras and IMU. Both are available. The only limitation is that if you're just using the poses, you can run the device using USB 2. But if you want the raw data, then you need USB 3, which is, we support both types of connection. Mm-hmm. But you just needed that for the bandwidth.
Thank you.
I have two small questions. Do you have relocalization on your model?
Yes.
So it's actually a relocalization. It's not like loop closure.
Well, the module itself.
Can I save a map and then relocalize?
Yes. The module itself is building a map. It has several dozen megs, dedicated to that, and you can actually download the map and use it later or with another T265, and the device will relocalize to the map.
Okay. And second question, so your IMU give about like 100 hertz, as I remember. Does your internal SLAM use 100 hertz or you use some higher frequency from IMU?
Well, the IMU is, I believe, the same between the 35i and the T265, and it provides 200 hertz for the accelerometer, I believe, and 260 for the gyro, something like this. And the SLAM algorithm is actually running at that speed. And we're only, updating when fisheye frames are available. We're only using them to update the estimation. But the SLAM itself, the poses are provided at 200 hertz.
Thank you.
Okay, any other questions for Sergey? All right, let's give him a round of applause. Sergey, great presentation. Thank you.